All right, welcome everybody to Chapter 6. We'll be talking about inverse trigonometric substitution here. So that's going to be our last technique of integration. What's nice about this technique is it applies to very specific functions, so you'll be able to tell right away this is an integral for inverse trig substitution. You'll apply it when we have this type of square root, so a constant minus x squared, a constant plus x squared, or you can also apply it if you have a constant plus x squared in the denominator, even if there isn't a square root. All right, so let's look at the first case. All right, so in section 6.1, we'll be looking at how to integrate integrals that have square root of a squared minus x squared. All right, our goal is to evaluate integrals which contain square root of a squared minus x squared using an inverse trigonometric substitution. We looked at this in the last chapter, so following what we've seen in the last example of the preceding chapter, of chapter 5, we'll use a substitution involving an arc sine function to integrate functions that contain, this should be a minus, square root of a squared minus x squared. All right, so let's try it with an example again. We'll have a recap of the method afterwards. All right, so let's say I want to integrate 4 minus x squared to the 3/2 dx. Now, you might be saying, I don't see a square root. There's a 3/2 here. The 3/2 is hiding a square root. In fact, this function is the same as 1 over the square root, and I'm going to put that to a power to the 3. All right, so here's the idea. I want to build a triangle, just like we did when we simplified inverse trig and trig functions mixed in. Do you remember? So we want to build a triangle with square root of 4 minus x squared as a side. All right, so I'm going to put my triangle. That might be a pretty bad triangle. It's going to have an angle. So I'm going to be using a substitution where this becomes my new variable. I want square root of 4 minus x squared to be a side. Because I have a minus here, it's going to be one of the two shorter side. I'm going to put it here. And then if I want to make sure that that's one of the sides, I'm going to put 2 for the 4 and then x for the x squared right here. Right, so here's my triangle. Now in that triangle, if I try to figure out what sine theta is, it's opposite over hypotenuse, and so that's x on 2. Cosine theta is adjacent over hypotenuse, which is square root of 4 minus x squared divided by 2. All right, so let's try this substitution. I'm going to use this right here. That means x is 2 sine theta. I'm going to send the 2 to the other side. So that's what I'm going to do to change my variable. So if I look at dx, I'm going to get 2 cos theta d theta. And then the square root that I have right here, I'm going to use this identity to replace it. So 4 minus x squared is equal to 2 cos theta. All right, so this is a bit strange. It's actually easier this way, but if you really notice here, theta is arc sine of x on 2. This is the substitution I'm using, but if we write it this way, it becomes much easier to apply to an integral. And so we kind of isolate x instead of theta. All right, so then my integral is the integral of 1 over 2 cos theta cube. That's this part. And then I need to replace the dx as well. For the dx, I'm going to use this one. So I'm going to get 2 cos theta d theta. I get 8, 2 over 8, so that's 1/4. 1 over cos squared theta d theta. I need to integrate this. It looks hard until you remember cosine is 1 over secant. So 1 over cosine is secant. So really I have secant squared, which is one of the basic integrals that we saw on one of the first days of integrals. So that's just tan theta plus c. And then when I need to go back to x's at the end, instead of using this, if I plug this in, I'll get tan of arc sine, which is not simplified, right? We spent an entire class in the first week learning how to simplify this, and it uses this triangle, so might as well just use this triangle. Tan of theta is opposite over adjacent, and so I'm going to get 1/4 opposite over adjacent plus c. All right. So whenever you want to apply this, whenever you have an integral with this kind of square root right here, this part will always be the same. Right? So you always start with x equals a sine theta. Dx will be a cosine theta d theta. The square root will be a cosine theta. So that will become automatic. This part is easy because you just replace everything. The part that's hard is after having done that substitution, you have a trig function to integrate. That's why we spend so long talking about what if sine has an odd power, what if cosine has an even power, and all of this. This is when we're going to apply that technique. And then at the end, again, just read it from the triangles. You guys know how to do it. All right, so let's recap the method. If you have an integral with square root of a squared minus x squared, you should use the substitution x equals a sine theta. So really the substitution, sine theta is x on a. And so opposite, hypotenuse, third side will always be this. All right, so in this case, you don't need to show Pythagoras just because it's always going to be the same. And so we know what's going to happen. We know exactly what we'll get. Then to get the x, you just differentiate this. So I'm going to get a cos theta d theta. The square root we read from the triangle, it's always going to be cos theta times a. And theta, if I isolate theta here, I'm going to get arc sine of x on a. So that's the substitution we're taking, but we're going to use this one because it's so much nicer to work with sine than to arc sine.